Alright, so here's iChem lesson 15 on basic heat flow. We'll basically cover with this lesson how you would do calculations based on an experiment that help to either identify a substance or understand how much heat is exchanged or those kinds of things. First, let's talk about heat flowing in and out of systems and how it causes temperature change. The factors that affect temperature change, there are 3 of them that you're asked to write down. The first one is how much heat flows in and out. How much energy is given. That affects, obviously, more energy, or maybe not obviously, but if there's more energy, you have more of a change in temperature. How big the sample is. A bigger sample might have require a lot more energy to change its temperature than a small sample. You know, for example, if I have a small pot of water and I'm trying to boil it, it doesn't take as long to boil as a big old pot of water because there's more water in there, requires more energy to change its temperature. And finally, how easily the substance changes temperature. This quantity we'll talk more in depth about later, but different metals or different substances change temperature easier than others. Day-to-day experience with this might be the aluminum foil that your baked potato is wrapped in compared to the baked potato itself. We know from day-to-day life experience that a potato just holds heat.
Please call 021. Ms. Tarvin, please call 021.
A potato just holds heat like crazy. It takes a really long time to bake a potato, but that potato will stay hot for a really long time as well, and that's, a property of a potato compared to the aluminum foil. You could put that thing in the oven, take it out from the oven, and it's back to room temperature nearly immediately. Okay, let's put variables to these quantities. So the first one, Q, is that amount of heat flowing into or out of the system. Its unit is in joules, typically. So when you're talking about Q, you have the unit of joules. We abbreviate joules with a capital J. M is the mass of the sample. Its unit is in grams, typically. We relate that with a lowercase g. C is called the specific heat capacity of the sample. This is a constant that is specific to every substance. Every substance has a unique, specific heat capacity. And this relates to its propensity to change temperature. How easily does it change temperature? And its unit is in joules per gram degrees Celsius. Something with a really high heat capacity is resistant to temperature change. It requires a lot of energy to change the temperature. Something with a really low heat capacity can change temperature relatively quickly. And finally, this change in temperature, the thing that we kind of keep mentioning over and over, because we're talking about factors about changing temperature. What is important to remember is that temperature is the only one of these things that you can measure. Obviously, we can measure mass, but I mean the things related specifically to heat and energy. We can't measure specific heat. We can't measure heat flowing. What we can measure is temperature and use that to help find the other quantities. So this delta T is the final temperature minus the initial temperature. The delta symbol we've seen for a couple days now, because we use this with delta H as well, means change in temperature or change in whatever it's applied to. Alright, so here's how you actually use this information to solve some of the problems. In this problem statement, you are asked how many joules of heat, this is your Q, are needed to raise the temperature of 10 grams of aluminum, that's your mass, from 122 to 55 degrees Celsius. This is not your delta T, but it will help you find your delta T. If the specific heat capacity of aluminum is 0.9 joules per gram degree Celsius. This is your C. Start by writing your equation. Q equals mc delta T. Once I have my equation, I'm going to write down all my variables and my unknowns. Q is what I'm looking for. M is 10 grams. C is 0.9 joules per gram degree Celsius. And delta T is your change in temperature. So it's T final minus T initial. I'm going from 22 to 55. So my delta T is 55 final temperature minus 22, which is the initial temperature. This is 23 degrees Celsius. 55, no it's not, it is 33. 55 minus 22 gives you 33 degrees Celsius. So now I have 3 givens and 1 unknown. I'm ready to plug it into my equation. Q equals 10 times 0.9 times 33. I plug this into my calculator, I will get, give me a minute to plug it in, second to plug it in, I will get 297, and the units on Q will be the whatever units of energy are in my specific heat. So here it's in joules, so my units are on joules. My answer to the question, how many joules of heat, is 297 joules. Okay, let's look at another type of question that might be asked. Real quick, I'm just going to write my equation again. Q equals mc delta T. And see if we can identify what we're given out of these things in the problem. It says a 1.6 gram sample, that's my mass, of metal that has the appearance of gold requires 5.8 joules of energy, that's my Q, to change its temperature from 23 to 41 degrees Celsius. That's not my delta T, but it will help me find that number. And you're asked, is the metal pure gold? So based on what I'm given M, Q, and delta T. What I don't know is C. I'm going to use C to decide whether this metal is pure gold, given what I know about gold. Okay, so kind of a not so clear way of asking you to find heat capacity first. But you know to find heat capacity because you're given M, you're given Q, and you're given delta T. That makes it a heat flow problem where you would use this equation, and your only unknown is C. So Q is 5.8. M is 1.6. C is what I'm looking for. Delta T is 41 minus 23, which is 18 degrees Celsius. Now I'm going to plug everything I know into my equation. For Q, I'm going to put 5.8 equals. For M, I'm going to put 1.6. For C, I can't put anything there. I don't know what it is, so I'm just going to leave it. And for delta T, I'm going to put 18. Now I have two numbers and one variable over here. I can multiply these two numbers together to sort of simplify what I'm looking at. Can't do anything with this quite yet, so I'm just going to leave it. 5.8 equals 1.6 times 18, which is 28.8 times C. Now it's just algebra coming back to haunt you. You have a variable you're trying to solve for, and it's multiplied by something else. You need to undo that math to get C by itself. To undo multiplication, we divide. If I divide by 28.8 here, I have to divide by 28.8 here as well. This cancels out. Anything divided by itself becomes 1. And I end up with C is equal to 5.8 divided by 28.8. So if I plug that in, I'll get my heat capacity is equal to 0.201 joules per gram degree Celsius. So I found my unknown in the equation, but did I answer my question? Go back and look. Is the metal pure gold? That's what I want to know. So I need to compare this number to the known heat capacity of gold, which is 0.129. This is not gold. And this is actually a method that scientists use to help identify metals in certain situations. In particular, actually, in a crime scene situation, if you're finding a metal, you might be able to identify it by doing an experiment that allowed you to find some of these variables, finding the heat capacity, and then matching it to known values. And we'll do an experiment with that at some point next week. Alright, so this is if you're given heat, temperature, mass, and you want specific heat. Alright, now, last version we're going to try right now. Same equation, Q equals MC delta T. But what am I given this time? Let's read the problem statement. What is the change in temperature? So what I'm looking for is delta T. If 150 grams, that's my M, of chloroform, what is the change in temperature of 150 grams of chloroform if it absorbs 1,000 joules, that's my Q, and the specific heat of chloroform is 0.96 joules per gram degree Celsius. That's my C. So I have M, Q, and C, and I'm looking for delta T. I can start plugging these equations into my formula. Put 1,000 in for Q, 150 in for M, 0.96 in for C, and delta T is what I'm looking for, so I'm just going to leave the variable there for now. And now I'll do the algebra. First I'm going to simplify this by multiplying 150 by 0.96. I get 144 times delta T. Now over here I still have that 1,000. I haven't done anything with it yet. Now I'm undoing this math. Delta T is multiplied by 144 to get delta T to stand alone. I'm dividing by 144 here. Whatever I do over there, I have to do over here. This will cancel, and I'm left with delta T is equal to 6.94 degrees Celsius. Okay, so in all three of these problems, we use the same equation, but you're solved for any number or any one of the variables is possible. So you can be given all three of the ones on the right side and have to solve for Q. That's the easiest version of these problems. Sometimes you have to do some algebra and you're given Q and asked to find one of these other three variables. You have to be given information about three of them and asked information about the fourth. But as in the case of this example, it's not always clear-cut. This example didn't say specifically, find the specific heat of the metal. We sort of had to read between the lines, look at what we were given, and decide what we needed to solve for. Come ready to do some of these problems tomorrow. Go back and watch if you need a little bit more help on certain things. Make sure you don't forget to go complete the Google form. Have a good night.